All right, welcome back. So the next objective of this section is to talk about absolute extrema. We have briefly mentioned it in the past videos, but we're gonna actually tackle the definition and how to find it in this video. So let's begin. In many applications, we have to try to find the actual global extrema, knowing the critical point or also the local extrema. It's not good enough. For example, if we want to make the greatest profit, we want to actually we want to actually find the absolute greatest profit of all, right? So how do we find the global? In other words, the absolute max and min. So there are a few additional things that we have to think about. A point that is a global max or a global min is going to be the higher, or in other words, lower, right? Depends whether you're talking about max or min, than every point on the graph. So these points come from the shape of the graph and the window through the view of the graph, right? We can kind of see that from the picture. So for example, if we look at this picture, we can see that assuming that this ends here, right? That this ends there. There's nothing beyond this line. That the function only exists from here to here, then we can see that the global, or in other words, the absolute max of this function will be the higher point on the graph, the highest point on the graph, which we know is going to be this one, right? If you notice, there's nothing higher beyond that line, right? This one, we see this is known as the local max as we've found it before, and it's not higher than this, right? Even this right here, it's higher than this local max. So what we're trying to do here is trying to transition to an idea of how to find the absolute max or the global max. So we can see here that we can also discuss the global min, or also known as the absolute min, and the absolute min will be the lowest point on the graph. There's nothing lower than this, right? We can see a few points that are local min, but local mins, right? If we want to distinguish between local mins and absolute min, local mins not necessarily are the lowest point on the graph, right? In fact, there's even more points that are lower than this, even this end point right here. So the distinction that we want to make is absolute min is the lowest point on the graph. Absolute max is the highest point on the graph. And we can kind of think about them in a formal way, right? So we can think about that the value of the function has an absolute max if f of a is the greatest value of the function for all the values in the domain of the function, not just for the immediate surrounding, not just the immediate surrounding, but everywhere, right? And the absolute min is the same idea. It's going to be the value of the function who's the smallest of all the values of the function for any x in the domain of f. And we're gonna say that f of x has an absolute extrema if f of a is an absolute max or absolute min. So extrema refers to both cases, right? Either one or both, right? So the local extrema of the function, we know that it occurs in the critical points. These points in the functions that we can find by just thinking about the shape or by using the derivative to help us. But if we're looking at the function in a closed interval, then the endpoints could be extremas as well. If you think about it, these endpoints could be these endpoints extremes are not related to the shape of the function. They actually have to do with the interval and the window through which they're viewing the function. So let me show you an example of this. We can see here that we have a local max, and that if the function of the graph is between C and D, right? That's the window of this graph. That there's nothing beyond that. Then we can see obviously that there's a higher point on the graph, higher than this local max, right? And in a similar argument, we can say that hey, if you look at this local min, we can actually see a lower point on the graph, and these actually happen in the endpoints, and the endpoints are not actually related to the shape of the graph, right? They're not related to the shape of the graph. We know that the shape of the graph determines whether you have a local max, a local max or a local min, but the endpoints are not related to any specific behavior of the graph. They just happen to be the endpoints. So, so the strategy that we're gonna talk about in this is that it's actually not so bad. Actually, what we need to do is just compare the values of the local min and the local max and the endpoints. So how do we decide if the endpoints are global max or global min? It's actually very easy. Simply plug in the endpoints along also with the critical numbers and just compare their y values. Just compare their y values, and that's just good enough, right? So let's look at another graph here, and we're gonna discuss a few things, and we're gonna review a few items that we have discussed before we actually jump into another type of problem, right? So in this example, we have just a picture of a graph, and we are asked to find different items of the graph. For example, the first one says, where is f prime defined? In this case, we don't have any place where it's undefined. F prime will be undefined if we had an edge and a corner, or if we had a point that had a tangent line that was vertical. So in this case, there is no such thing as that. So does not exist here. The next thing we're gonna find is what are the critical values of f. Well, we know that critical values happen at when you change directions. Maybe I can put this in a different color, but we can see here that it happens in here, 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 and here, and here, right? And assuming that this right here is actually there's a tilt, there's a curve going on that we cannot see very well. So what we're saying here is that there's critical numbers at x equals -2, comma, -1, comma, 0, 1, and 2. Those at x values at -2, x value at -1, x equals 0, x equals 1, x equals 2. Those are all critical numbers, right? And we know those critical numbers because that's where the derivative is 0, right? The derivative is 0. Do we have any local min? And we do, right? We know that local min are where you go from decreasing to increasing. So that's right here. Decreasing to increasing. That's right there. And right here, right? Decreasing to increasing. So we have 3 points in here where we have a critical number. And the locations are x equals -2, 0, and 2, right? Again, these are not the local min. These are where you find them, right? Where does the f have a local min? This is the location. If you want to find the actual local min, you have to look at the y value of this. The y value, which will be what? 1.15, I don't know, something around there, right? But we're not focusing on that moment in this right now. What about the local max? If we look at the local max, that's gonna happen here and here. So that's at -1, x equals -1, x equals +1. So those are the locations where you're going to find local max. What about the global minimum? Well, do we have any global minimum? And yes, we do, right? We have a global minimum. The global minimum is the actual value of the function. And that happens somewhere in here, right? So that lowest point on the graph. The lowest point in the graph, if we see here, that's the lowest point in the graph, and it actually happens somewhere around -1.25, right? Roughly around that area, -1.25. 0.25. That's the value of the function. And where does it occur? It occurs actually at two places. It happens at negative 2, at equals at x equals negative 2 and x equals 2. So x equals negative 2 comma x equals 2. What about what is the global maximum? Where, well, these are not global max because there's a number higher than that, right? In fact, this actually is going high and keeps going up. So it gets higher and higher without any limit. So it's just gonna keeps going up. So there's no definitely a point where it is the highest point of the function. So therefore, this is the example where the global max does not exist. So where does it occur? Well, since it does not exist, it does not gonna happen anywhere. The last part is asking us to find where is the derivative greater than 0. So pretty much is asking us to know when is the function increasing or increasing, right? Or where the derivative is 0. So that happens. So we can highlight it. That is increasing in this region, and then increasing from here to here, right? But they're not asking us. They're asking us where is this happening? Where is this happening? So it happens from negative 2, right? If I it's from here negative 2 all the way to 1, from 0 to 1, and from 2 to infinity, right? So it happens from negative 2 to negative 1, and from 0 to 1, and from 2 to infinity. There you go. And then lastly, we're gonna find where is the function, where is the derivative less than 0, which translates to where is the function decreasing. So let's use another highlighter. The function is decreasing from this direction all the way to here. Is decreasing from here to here, and then decreasing from here to here. There you go. So it's decreasing from negative infinity to negative 2, and then from negative 1 to 0, right? And from 1 to 2, right? Remember that happens from here, negative infinity, all the way to 2, from 1 to 0, and from 1 to 2, right? So those are the intervals where the function is decreasing. That's the location where it's decreasing. Also, we want to make sure that we say that this is union instead of a comma. Okay, right? We unite these intervals. All right, so that was it for this problem. I hope you guys found this helpful. Please let me know if you have any questions.